Is it okay to start?
So hi, good morning, everyone. Thank you for coming. I'm Claudia. Today I'm here with Dadan, and we're going to talk about bridging on PoS sidechains with Ethereum. So as first slide, just some motivation introduction. As many of you will know, many crypto projects are being built as sidechains to Ethereum. This is due to the classic issues of scalability, interoperability, or upgradability. But we would like to focus on the single-purpose sidechains, as we consider them that they bring lightness and agility to Ethereum, and they add capabilities and functionalities without branding to Ethereum. However, any sidechain, when you're working with a sidechain, you must guarantee some security awareness. You need to guarantee a secure interaction, of course. At first, any sidechain is vulnerable to civil attacks. And when not sharing the consensus algorithm, sometimes it's hard to guarantee the updatability. So the talk structure is going to be, we're going to talk about bridge interaction, like very basic, then transaction verification, block headers reporting, which includes the voting committee selection and Finality Gadgets. Then we'll talk a bit about BLS and how they improve efficiency. And to finish, just with the bridge workflow and to sum up. So now Adam is going to talk, and then
Thank you.
I'll be back.
Okay. As Claudia said, we are talking just for you to have some context. We're talking about single-purpose sidechains. In this case, we will showcase these sort of protocols through example, which is Witnet, which is what we are building in Stanford Labs, which is a decentralized Oracle network. So think that this actually works for many different protocols, but for the sake of having a specific case, you can simply imagine how some terms that are specific to Witnet would translate to your own protocol of choice. So Witnet, in this case, is a single-purpose Oracle sidechain. Oops. Okay. In Ethereum, and it's incentivized by token rewards, and there's an algorithmic reputation system. So basically, there's a system that tracks the performance and the reliability of the nodes in the network, and we will explain later how it works and why that's important, and why protocols that use this scheme of sidechaining to Ethereum through this system should have something in that line. In this case, we are talking also about fully permissionless protocols, okay? And particularly also about sidechains that may or may not have their own token, okay? It's not an assumption that it needs necessarily to be the kind of sidechain that uses the same token as the main chain. So what's this? What's bridge interaction? We call bridging to the fact that in some way you need to peg one chain to another or connect one chain to another. You need to some way to communicate both chains, the side chain and the main chain. And this communication, in our case, is achieved through a contract that needs to exist in the Ethereum main chain, which we call the WBI, the Witnet Bridge Interface, but for short, it's a bulletin board where you want to, it's just for posting, in this case, data requests, so the tasks that you want to offload into the sidechain, into this sidechain that will act as an oracle, but you can think of things of very different themes, like, I don't know, like Golem or Filecoin or things like that, where you have like a sort of second layer protocol that is single purpose for doing some sort of computation, and just you just care that you want to get the result back at some point with some guarantees. So who's in charge of that communication? That's the bridge nodes. The bridge in a classical sidechain scheme or something like a drive chain, you would have miners being mining into in both chains, but in this case, if one wants to not to rely on proof of work or even on proof of stake, there are alternative schemes, which is what we are exploring here. In this case, these nodes relaying transactions from one chain to another will need simply to monitor the status of the contract, of the bridge interface contract, and relay the requests from one network to another. And when the requests have been resolved, they will be in charge of relaying their results back. It's important that they are economically incentivized to do so. In this case, the way we would love it to work, and the way it works, is by having these nodes earn ETH, which is paid as fees when someone requests data from Ethereum contract and spend with, in our case, but in any other case, the token that is native to the sidechain, which could be ETH also. So that's indeed the most robust way to do it. And then there needs to be some way to selecting which nodes will be in charge of doing that, because we want the bridging scheme to have the same degree of permissionlessness as the sidechain itself or as Ethereum itself. And for that to happen, we need to have some mechanism for choosing those nodes. And in our case, we decided to go with a verifiable random function, which is a novel cryptographic tool that we have today that is being used also by Filecoin and Algorand, and it's becoming more and more common. And the idea is that we can basically do this sortition, select from a pool of bridge nodes, select a few of them, and that will by turn be in charge of relaying the transactions. Then if we want to relay transactions from one chain to another, we need to have some way to verify those. So we use something that everyone will be familiar with, SPV, Simple Payment Verification. It's a protocol that has been used for more than 10 years. It's pretty common in, not Cefu, in Bitcoin, for example. And the idea is that I can prove the fact that some transaction was included in a block by simply providing a Merkle path, which is the minimum set of data that you need to prove that the cryptographic commitment from one transaction to one block. That's exactly how light clients are created, and that's the point of using a Merkle tree when creating blocks at the end of the day. So the idea is that you can present a very compact and efficiently verifiable proof of inclusion that proves that transaction actually comes from Witnet, and that's the result for the data request. If you think of any other protocol, proving that that's the actual result from one request sent to that. Obviously, if you want to verify against blocks, transactions against blocks, transactions against block headers, you need to have some knowledge of the block headers in the main chain, inside in our case, the bridge interface. So you will probably need to bundle some block relay scheme in there. So basically what you are doing is replicating, in our case, if we have on one side Ethereum and in the other side the Witnet chain, we need to build a light Witnet client inside a Solidity contract and an EVM contract on Ethereum, okay? So the way it has to access those block headers is having those block headers to start on this EVM contract. And for that, we can leverage the same reporters, the same set of nodes that will be relaying the requests and the results from one side to another. And we need to provide some incentives for them to do that also. And for sure, we will have to handle chain forks, finality, and so on, which Claudia will explain later, and it's really awesome how it works. So for a really, really easy example of how this kind of relaying works, with Witnet is a little bit more complex, but at the end of the day, it boils down to a scheme which is very similar to the BTC relay, which is something that has been operating for years in Ethereum, and basically something that allows you to verify Bitcoin transactions from Ethereum contracts. And the mechanism is quite simple. Basically, there are relayers submitting Bitcoin blocks to this contract that exists in Ethereum. And as Bitcoin is using proof of work is super easy to verify, super efficient to verify. You just need to do some hash of some nonce and some data, and you just verify that, and you can follow the same logic for the fork choice rule inside the Ethereum contract. So you can simply have a probabilistic finality after a while, and so on. You're already familiar with that. The thing is that from that moment on, any Bitcoin transaction can be sent to the contract for verification. It's actually it's a call, so it's free. It would be free. The only thing is that these are done through transactions because you want to incentivize the relayers to send the blocks. So the idea is that when someone sends a block to the block relay, they are promised that they will get a share of the fee, or they will get the fees for any transactions that are verified against that block. For any transaction that belongs to that block, every time someone verifies a transaction that belongs to that block, they will get this small fee. So the problem comes when you're not using proof of work, when you're using proof of stake, or if you are using things that are not necessarily proof of stake, but more in the lines of BFT protocols. So in that case, verifying is not that easy, and you have difficulties with finality, and you will probably need to have a lot more context and information on what's going on the sidechain, what's the state, the world state, and Claudia will explain later. So the problem here, obviously, with non-proof of work chains is that you can trivially forge block headers that may include or exclude transactions of your choice if you're an attacker, and you could basically construct a proof of inclusion for those transactions and for the made-up header. And that would be very easily feedable into the WBI, and it would accept it, and it would store it, and you have basically forked this contract from the actual sidechain. So we don't want that to happen. So how do we solve that? So there are two important things for preventing that. One is really finding a really smart and sensible way to have these voting committees. So basically make the nodes of the sidechain vote or attest what's the status of the system and where the chain is, what's the best block in the chain, and so on. And then having some Finality Gadget, which is some mechanism for having reasonable finality and an eventual finality. So Claudia will explain how, how it actually works.
Right. So, as Adan just said, one of the most important parts of the integrity of the block headers to be reported is selecting the right voting committee. At first, when we had this discussion in WITNet, the first thing that came to our mind was thinking, why not bridge nodes, since they were already connected and in touch with the WBI. But as WITNet is fully permissionless, this was a set of nodes that were easy. They could be attacked by civil attacks. And then why not then just the known identities in WITNet? Well, this is hardly scalable because, of course, you don't know how many nodes you have, and you can't limit the nodes of someone just spinning up nodes. So we decided to have the active reputation set, as this was the set of active nodes that have proved that they had an honest behavior in the last epochs. For us, that we use in WITNet, a reputation system was, this was a good set, but of course, depending on the sidechain that you're using and the consensus you have, this could change. But the thing is, there are honest nodes that you trust. And because of BFT assumptions, you know that at most 1/3 of the nodes will have a bad behavior. Then we added a collateral and coinage in order to prevent other attacks. And we know the RS is limited with respect to the velocity of the network. That didn't happen with the known identities. So the ARS, the important thing is that is the set of the nodes that are going to be in charge of proposing block headers to the block relay. So the next thing to study was the Finality Gadget that we wanted to have implemented. So the problem here is we have a block or a block header that has been finalized, voted for enough members of the voting committee. That would be this one. And then more block headers are being proposed, supposing chains A and B, so a fork happens, and how do we manage this situation? So today what I'm going to do is just explain in a very simplified way the solutions that have been implemented in Cosmos, Kasparov FFG, and Grandpa. So for Cosmos, is a very simple way to do and manage this situation. We have end reporters, and unless at least two-thirds of the voting committee agree on a block, you don't get finality. So the block is stopped until you get those two-thirds. So suppose we have 100 reporters. In these situations, we have 50 of them voted for chain A and 49 for chain B. Then the block is just, as I said, I mean, the chain is stopped until you get the two-thirds. So they need to keep voting until they get the two-thirds. In this case, for example, they get 80 for chain A and 20 for chain B. So the chain A is set as the good one, the valid one, and this new block here is set as final. So, of course, this is a very nice and simple way to do it because every block gets the two-thirds, but it suffers from liveness. So another approach was the Kasparov FFG. This is for sidechains that may have high velocity of the network, and in which you would need to get finality of a lot of blocks. So what they do is that they select the checkpoints that would be a set of n epochs. So every n epochs, the reporters or the voting committee needs to vote to get finality. Again, you have the two-thirds. So when a block gets the two-thirds of the votes and they agree on a block, the blocks between the checkpoints are finalized as well. So this is nice, but the thing here is that there exist blocks that they per se didn't get the 2/3. In the end, Grandpa is another approach similar to the one in Cosmos. Again, we get the 2/3 of the votes in each block that has been finalized. But what you do here is you can continue voting. So for example, here, suppose we have n reporters that at some epoch, 20 of them voting for chain A, 30 of them voting for chain B. Then they can continue voting, and you take into account the rest of the voting committee that didn't vote at the first epoch. So you take, for example, at chain A, another 5. In the next epoch, 25 for, in chain B, another 5 in next epoch for chain A, and another 15 in chain B. So in the end, you count, and when you get the 2/3 of the voting committee, if we have 100, this would happen in chain B, you consider as finalized the first block of the chain that you set as valid. And meanwhile, the other chain, in this case A, is just cancelled. And then you start again with the same procedure for the next epoch. So just a quick recap of what we have seen so far. We have the WBI, this contract in Ethereum that is in charge of the transactions between, that has the transactions between Witnet as a sidechain and Ethereum as a main chain, that needs to have some knowledge of the block headers in Witnet, and for that we have the block signers or voting committee, in our case ARS, the active reputation set, that vote for a new block header, and when they get the 2/3 is added as a new block header. So now I'll talk about BLS, but very quickly. The classical thing that we have here is if we want to report and take into account counting the block headers that have been reported for the voting committee, usually what we have is that every node in that set is proposing a block header, and then you have to verify every signature. Then you get, once they are verified, you count the block headers that have been reported and see if they agree or not. So the thing here is the cost is very high if you have a big number of nodes in the committee, in the voting committee set. So this would be, that cost 40K per each, the number of nodes that you have to verify. So what we like to have is, in some way, have just one verification to verify each of the members of the set, and this can be done using BLS, which the gas cost is 500K. So it's a great solution when having a lot of signatures to be verified. But the procedure is very similar. We just have one verification and then count again the block headers and apply consensus. So when speaking of BLS, you always have to define the pairing functions. These are basically functions that send points from two elliptic curves to the natural numbers. And the thing is, they have two properties. The first one is quite natural. It's that they are bilinear. When you multiply a scalar for one of the arguments here is equal of multiplying that scalar in the other argument, and when you do the sum of two arguments is equal to the product of the two pairing functions. And the second property is that when you multiply each argument for a scalar, you get the pairing function power to a times b, being a and b the scalars. So the thing is just that they have nice functions that they have two properties. So what we can do with these pairing functions is verify a signature. Just need to satisfy the equality that pairing function of the public key and the hash needs to be equal to the pairing function of the generator of the curve and the signature itself. So the arguments that you use are just the same as in the typical signature verification. So the nice things, well, yes, sure. And this is guaranteed by the first property of the pairing functions. Yeah, and the nice thing here is that doing just the same, we can verify a finite number of signatures. So suppose we have, we can consider P as the sum of, if we want to verify n signatures, so P would be the sum of these n public keys, then S the sum of the n signatures, and HM the sum of the hashes of the messages. So we just need to verify that the pairing function satisfy the equality of was just the same. This can be proved for the same properties that I just explained, but I don't have time to explain them. But anyway, the idea is that you can verify a finite number of signatures just with one equality. So just to finish, just summing up the workflow of the bridge in WithNet and to have a recap of the main ideas that we had in this talk. So first, we have the WBI contract that is in charge of receiving the transactions from one to another and in charge of monitoring this interaction are the bridge nodes, as Adam explained before. Then, for these transactions to be verified, you need to, the WBI needs to be aware or needs to have some knowledge of the block relay, the block headers in WithNet, and these are stored in a block relay contract. Using these are easy, you can verify them very easy using the Merkle path and the SPV protocol. So then for the block header reporting, you have to select a proper voting committee. In our case was the active reputation set. The signatures of those members in the set are verified using BLS. Then you check consensus, count the numbers of block reporters, and when you get the 2/3 and finality is applied, you can add, you can, the block header is added to the block relay contract. I think, yeah, I hope everything was more or less clear. I know that this talk had a lot of context, but we tried to explain as nice and easy as possible. So thank you very much, and hope we can see you tomorrow in our last talk that my colleagues are presenting. Is at 5 to 4 about the Radon, the domain-specific language for in WithNet for specifying the data requests in WithNet. So thank you, and please, if you have any questions, we'll be happy to answer.
No one's brave enough. Okay, we will be happy to answer any questions that you may have. We will be around for the full day and tomorrow. Thanks for coming. Thanks also to the whole WithNet team, which are the actual magicians that made this possible.